Dear students, let us continue our video lectures on advanced digital signal processing. I am sharing the screen. In the previous video lecture, we have discussed on discrete Fourier transform. We have seen some of the key connections or the takeovers from discrete Fourier series and discrete time Fourier transform while defining discrete Fourier transform. Okay, we for discrete Fourier series and discrete time Fourier transform, we have seen how the discrete Fourier transform equations are defined. How do they enable us for effective representation, frequency domain representation of aperiodic discrete signals? Okay, and from the small set of or same set of discrete samples in frequency domain or discrete frequency quotients, how do we get back or reconstruct back the time domain aperiodic signal? Okay, this makes a very compact representation because we have n aperiodic time domain samples which are usually occur in all the applications, and there we have exactly n coefficients while representing it, and it is a discrete representation as against the discrete time for a transform where there is a continuous representation of Fourier spectrum in frequency domain. And this discrete representation with exactly same number of samples as that aperiodic time domain signal, okay, enable us with projection onto the corresponding inverse basis functions, exponential discrete exponentials, will enable us to get back those n samples in the n time domain. Right, we have seen some properties and some examples how exactly they in terms of properties, what is the similarity with respect to the discrete Fourier series properties and discrete time Fourier transform properties we have discussed. Okay, and we said that there is one property which needs more attention, that is the convolution to multiplication or multiplication to convolution property. We also have discussed at any instant of time, at any location or at any instant, if you would like to take a signal out of the range of 0 to n, which is usually a range of aperiodic signal that is available, when we need to apply discrete Fourier transform, we said that we need to bring in the samples to that range because there is an underlying periodic sequence, and so any minus n operation or any operation that brings in the signal to out of 0 to n range will put it back to that range through modulo n operation to perform or conveniently apply discrete Fourier transform, except that there is no change in the properties as discrete time Fourier transform, and this modulo n operation is leveraged from discrete Fourier series. Okay, that is taking the periodic 0 to n time instances of the periodic signal, right, or 0 to n frequency instances of the periodic signal, underlying periodic signal in DFS. Okay, so now let us discuss further on the convolution to multiplication or multiplication to convolution property of discrete Fourier transform. So let us start our discussion. If we have with, say for example, x1 of n, okay, and x2 of n, both are aperiodic and discrete signals. Okay, so let both be aperiodic and discrete. Okay, signals. Fine. So in that case, if we perform convolution here, what will happen in the frequency domain depends upon what kind of transform we take. Say if we take discrete time Fourier transform, what do you expect? If these are, since these are aperiodic and discrete signals, okay, we will have x1 of e power j omega, that is discrete time Fourier transform multiplied with x2 of e power j omega, right? Whereas if we assume that if x1 of n, even though it is periodic, if it is made if it is even though initially it is aperiodic, if we make a periodic signal from it, okay, that is repeating it same with the length of the sequence. Okay, so with the period being the length of the sequence, x1 tilde of n, now convolution with x2 tilde of n. So first of all, this convolution itself is not possible because both are periodic signals. In that case, we, in while discussion of discrete Fourier series, okay, what did we tell? The convolution is not possible, but we can take a periodic convolution. What does this periodic convolution do? If for simplicity, let x1 of x tilde of n, x1 tilde of n, and x2 tilde of n have same period. Period that is equal to same time period. Okay, that is equal to n of n. Okay, so and hence you can easily define periodic convolution and so on. Okay, so what did we said as periodic convolution is, so how did we define periodic convolution? Let us bring in that expression here. Okay, so we would like to write everything in the range 0 to n minus 1 in periodic convolution, and hence let us keep the variable, the running variable, let this be r is equal to 0 to n minus 1 and rm. Okay, so which is usually used x1 tilde of m into x2 tilde of n minus m. But this will go out of the range of 0 to n, and hence when we write the periodic sequence, we can take the corresponding samples in 0 to n minus 1. Okay, please note that. However, okay, so when we write, when we want to take all samples in a 0 to n minus 1 range, then we write the additional operation, that is modulo operation. As we discussed in the previous video lectures as well, this modulo operation, n when we write, there is no need of writing this tilde. Okay, this tilde can be knocked off. Okay, so we can write this now for writing the with aperiodic and discrete signals of duration, okay, each with each 0 to n, okay, each x1 each with 0 to n minus 1 or period n. Okay, we can write this as since we are considering only duration 0 to n minus 1, we should write modulo n here. Okay, so this is in terms of DFS, and this is x3 tilde of n we can write, and this is x3 of n I can write. And what is the length of the sequence x3 of n? The length of the sequence x3 of n is only n. Okay, this length n. Okay, so here also the sequences of length n. Of this is not period n. Please note that this is sequence of length n. I request you people to note the differences. When we write the discrete Fourier transform, what we need to deal with is discrete signals, aperiodic signals only. There may be an underlying periodic sequence and the transformation may be guided by them. Okay, but however, we deal with aperiodic discrete signals. While in DFS, both are periodic. Okay, in time domain and frequency domain. Okay, while in conventional discrete time Fourier transform, both are aperiodic, and there is no underlying periodicity while defining the transform. Okay, that those are the differences, right? So, and in this case, okay, so of length n, so you can see that this also comes from one period of x tilde of n. Fine, but you can see here, this here when we define like this is usually referred to as circular convolution. So this we have defined it as periodic convolution. Okay, because there is a periodicity. Because of periodicity, there is no need to write modulo n here. You can pick n minus m. N minus m also exists here for any m. Okay, and n. Whereas here n minus m doesn't exist because the sequence we are looking at is only 0 to n minus 1 region. Okay, and hence, but still we want to imitate what happens in the periodic sequence which extends from minus infinity to infinity. Okay, that's why this modulo operation has come here. Okay, so please note that, and hence this is called periodic convolution. Okay, whereas what we do here is a linear convolution. Okay, and this is periodic convolution. Okay, let me write complete writing. Okay, because of the nature of the convolution we take from the periodic sequences. Okay, we can't take from minus infinity to infinity. We would like to take only in the range 0 to n minus 1 or n samples. But in that range, whichever the samples after shifting are falling, okay, are being convolved. Okay, are being multiplied for getting the corresponding, okay, computation of the convolution sum. Right? Similarly, now, what do we call this is circular convolution. The reason being, here there is no periodicity involved as such. But how are we computing this convolution sum? By assuming that these samples, okay, these samples are like as we discussed here, these samples are in a circular like circularly spaced in time or in frequency, and then the shift also happens. Okay, while the shift happens, the change is from one location, shifting from one starting, instead of starting from here, we would start the signal to understand from here. Okay, so either the time shift or the frequency shift are taken with modulo operation to imitate the periodicity that is underlying for defining the DFT or DFS. Okay, for defining the DFT or DFS, you need periodicity that is being imitated by modulo n operation, and modulo n operation reflects a circular shift while doing any shift. Okay, so thus this convolution is done with a circular shift. Okay, you can see that this is known as, this shift is a circular shift now. Okay, induces right? Due to this circular shift, we call this a circular convolution. In fact, the periodic convolution or circular convolution are same. However, periodic convolution is performed with taking the finite length sequences, aperiodic sequences. Okay, while the circular convolution is computed with finite length sequences, aperiodic finite length sequences with n points. Okay, n points meaning the sum is from 0 to n minus 1. Okay, so while the periodic convolution is computed and considering there is an underlying periodic sequence, right? And the concept of shifting there is shifting the periodic sequence, not shifting in a circular way. Okay, but if we sample 0 to n minus 1, it is equivalent to shifting in circular way, right? So both are equivalent. However, the background for the way we compute this is different, because one we assume they are periodic sequences, in other way we assume they are aperiodic, but the shift is circular. Okay, hope you got this point. And there is another thing here to discuss. See here, for simplicity, we have assumed that both are periodic with period n. However, okay, these two sequences may be periodic with period n1 and period n2. In that case, we have to initially define which is the say higher period with which say n2 if it is larger than n1 and n2. With n2, we can take the circular periodic convolution, or with n1 as well we can take, but we need to define a priori with what period we take. Usually we assume that both are same periodic, so that the computing periodic convolution directly reflects in the frequency domain whatever we like multiplication of the discrete Fourier series of x1 and x2, right? Or we can take the maximum, assume maximum period, wherein the other signal we assume that there are zeros to fill that maximum period. So if n2 is greater than n1, so from after completing n1 samples in x1, remaining samples can be filled with zeros, right? Okay, and similarly here as well, you can come if n1 and n2 are two different lengths for the sequences, aperiodic sequences x1 and x2. In that case, you can take either only say the circular convolution with n1 points or n2 points. Usually, the higher than these 2 points are preferred to have a frequency domain representation conveniently. Okay, we will discuss the implications of the discrete Fourier transform of this x3 of n now. Okay, so far we have not discussed what will happen if we do a circular convolution in time domain. How does it reflect in the frequency domain? Okay, we will come to that discussion now. Before we discuss that, let us write what will happen in this case in the frequency domain. If I take DFS now, what do you write? X1 of k multiplied with x2 of k. The question here is, okay, so are these two, say if I directly sample this, so let this be is equal to x3 of e power j omega. Okay, and if I directly sample this, omega equal to 2 pi by some n into k, do I get, the question here is, do I get, okay, it's a question mark here, do I get x3 of k, which may be, okay, defined as x1 of, which can be defined as x1 of k into x2 of k. Will these two be same? That is the first, that is one question. Okay, the next subsequent question is, see if I define this as, okay, let me write the title of this slide as convolution. Okay, different convolutions. Yeah. Okay, and relating them, right? Okay, so if I define now this as, say, x3 of, so I have defined x3 somewhere, right? So let me define this as x4 then. Okay, x4 of n is equal to this. Okay, and x3 tilde of n, anyway I have defined this. x3 also I have defined here. x3 of n tilde of n as this. The question is, okay, will these two be same? Can these two be same? Okay, when will they be same, if at all? Okay, these are the questions we have with us. Okay, so there is one, say for a periodic discrete signals, what we have defined earlier is the only discrete time for a transform. Okay, and that apart from that, for periodic discrete sequences, we have defined discrete Fourier series. We have seen that the multiplication in frequency domain amounts to circular convolution in time domain. Okay, in the previous discussions. So now the question is, will this circular convolution in time domain, whatever the signal we get, will this be equal to a periodic linear convolution? Okay, and similarly, whatever I get in the frequency domain, can this be understood as a sampling of this the convolved multiplication of these spectrums? Okay, let us take one question after the other. First of all, let us discuss about it. Will these two be same? Okay, ideally we have started with, say, both are having period capital N. Okay, so if this sequence of length n, this is also of length n, assume that, what do you expect the length of x4 and b? Length of x4 and b, n1 plus n2 minus 1, that is 2n minus 1. Whereas the length of x3n, what is the length of x3n through periodic convolution? It is only capital N. Okay, and this is 2n minus 1 and this is capital N. So no way these two can be exactly same. However, there may be related because these sequences and these operations are related. Okay, we have also seen that under some constraints, these can be considered as sampled version of any of the frequency domain representation, discrete time Fourier transform representation. Sampling of it is equivalent to discrete Fourier series representation under some conditions. Okay, given those, let us see when these two will be same, can be same. Okay, or is there anything necessary to do, like to extract from here to here or here to here? Okay, let's discuss that in the next slide. So now we try to bring in, we have defined in the last slide what is periodic convolution, okay, and what is circular convolution. Okay, that's what we have done. Now in this slide, let us look at the relation between circular convolution and linear convolution. Okay, so why did I leave this periodic convolution? The reason being, see, this is anyway periodic signal. Okay, so in the worst case, even if this is somewhat related to this, it has to be x3 of n. Okay, so we should say here or, okay, let us write with same black, or x3 of n, because one period of it. Okay, so the main relation that we need to look at is the relation between x4 of n and x3 of n. Okay, convolved linear convolution and the circular convolution, not the periodic convolution. Okay, so that's what we are trying to see now. Okay, now let us define the linear convolution and circular convolution and try to see, is there any analogy or if when they will be like, can one be extracted from other? Okay, let us define first the linear convolution by x1 of n. For simplicity, assume that all are length n. Okay, x2 of n. And then we have a discrete time Fourier transform. Okay, and which gave us x1 of e power j omega into x2 of e power j omega. Okay, and let define this as x3 of e power j omega. Okay, and here let us define this as, so x4 of n, just to be consistent with our notation. And hence the length of this, so let us write the lengths of these sequences. Okay, so lengths, let us write with some other color. Okay, so length, so n, so the length of this is This is n. Okay, this is also n, and then this is 2n minus 1. Okay, length, right? 2n minus 1. And anyway, what's the sequence? This is 0 to 2 pi. 2 pi continuous. All are 0 to 2 pi continuous. Okay, right. Okay, so now let us write the other relationships. So we have here x1 of n. Okay, so when we want to, here we want to compute discrete Fourier transform. Okay, and hence what we have seen, we have not, since we have seen that the discrete Fourier transform is nothing but one period of the discrete Fourier series, we can directly take from there and write. Okay, what will happen? So if I have here x1 of k multiplied with x2 of k, okay, both are discrete Fourier transforms. Okay, taking one period, what will happen here is, instead of circular convolution, I will put instead of periodic convolution, I will put circular convolution. Okay, discrete Fourier transform, right? So please note that the lengths are same, whereas here the sequence length. Okay, so here it is also n. Okay, x1 into x2. This is also n. Okay, n and n. Okay, let us define here is equal to, for simplicity, x3. For time being, you take x3 of k. Okay, we will see if there is anything needed. Here is equal to x3 of n. Let us define this. Now, if I define it as n point circular convolution, okay, as I said here, okay, you will be shifting circularly, okay, n minus n times or n minus 1 times, and then performing this convolution operation. Okay, we will see an example for doing this, but you can easily note from this operation. Okay, instead of starting from here, we'll start here and so on, from here and so on, to get the sequence and then do correlation. Okay, so the length of this will be again n. Okay, because you are performing circular convolution. That means you are restricting yourself to 0 to n minus 1 range, and you are doing it for n minus 1 shifts in addition to the current 0, like correlation at 0. Okay, so you convolution at 0. So you have got n sequence. Since these two lengths are different, there is no way that these two be exactly same. However, we want to see, because of the frequency sampling, what will happen, right? So let us now take the frequency sampling aspect. See, assume that x3 of k is uptime from x3 of e power j omega sampled at 2 pi by n into k, right? This implies what in time domain? This implies that, see, x. So for simplicity or for better understanding, let me define this, okay, as x4. Okay, exactly like we have defined this convolution is x4 like x4 of n here. So it's Fourier transform, we define it as, okay, x4 here. Okay, so please note, however, that, see, if I sample x4, it means that, okay, I am exactly sampling x1 and x2. Okay, so and hence I will interchangingly will be writing x4 or x3 e power j omega. Okay, because of this definition, it comes x4. Okay, if I take discrete Fourier transform for x4, I will get x4. Okay, whereas to get, so let us stick to that itself then. Okay, right. So I define x3 of k as sampling this x4, okay, rather than x3. I can define like this, right? X4, because this indicates that x4, if you see right hand side and left hand side, x1 of k into x2 of k. Okay, here if you see x1 of e power j omega sampled at omega equal to 2 pi by n into k. Similarly, this is also sampled at e power j omega equal to 2 pi by n into k, right? So they exactly agree. So there is no problem in defining it as x3 of k equal to x4 of e power j omega, right? So, but however, if you take now frequency domain representation, so what do you get? Is the question. So let me write with a little darker color and different color. Okay. See, x4 you are sampling. So x3 of n is equal to what will happen? See, you are sampling with period of capital N. So the repetition of x4 of n, okay, should happen at period of capital N, irrespective of length of x4. Okay, x4 of n has to repeat, okay, yet capital N, right? This is what happens for getting x3, right? What you get is x3 tilde of n. Okay, because any frequency domain to time domain brings in the periodic signal. Okay, so since it is discrete in, it is the discrete in frequency domain, you will be getting a periodic signal in time domain. Okay, that's what happened here. Let's see if I can, yeah. Right, you can see that irrespective of the length of x4, it will be periodically repeating at intervals of capital N, because I sampled this x3 of e power j omega, x4 of e power j omega at n. So now what does it happen? See, anyway, here if you see, okay, here let us see, here m is what? Length of x4. So length of x4, let us write again the length. After writing lengths, let us see, because of these lengths, aliasing does it happen or not? Okay. Yeah. Sorry. Okay, length of this is n, because period. Okay, since it is periodic signal, let us write it as period rather than length. Okay, n, and length of, whereas period of this is n, and length of x4 of n is how much? Is 2n minus 1. Okay, that is m is equal to 2n minus 1. And hence, will the aliasing happen or not? Surely will happen. So, how do you relate now x3 of n and x4 of n is the question. So, circular convolution, if you see n samples of circular convolution, can be considered as the time aliased versions of the linear convolution results. Okay, so that means how many samples they get time aliased? Okay, they will get aliased for after n samples, right? So now if I extract x3 of n, so if we now see x3 of n, time aliased version of what? Of x4 of n, right? That implies what? So over through this discussion, we see that, right, the circular convolution result how many points? N points circular convolution of n point sequences is time aliased version of what? Time aliased version of me write from here. Okay. Time aliased version of what? Of linear convolution. Right? Right. So this you should be able to understand. So this is the main thing that we that is intake, like that we can take from this slide, right? So the n circular n-point circular convolution of n-point sequences is time erased version of linear convolution. Now let us see. Anyway, we'll discuss further with some examples of circular convolution and so on. Okay, but let us, to understand this in more details, let us have a small example. So let the this example be very simple. Okay, so this is, let this be the sequence, that is, say sequence 1 x1 of n. Okay, and then 0 1 2 3 4 no 5 samples. Okay, so and then zeros anyway, so leave it. Okay, so to simplify this, let us sketch up to here only. Okay, this is sequence here. Similarly, assume that x2 of n. Let this also be n-point sequence, right? So for simplicity, let us take this. So because we can easily write, so what will happen in convolution and so on without computing. Right? We have taken exactly same sequences as well and same length. Okay, so n1 is equal to n2 is equal to n is equal to 5 here. Right? And hence directly we can write x3 of n or x4 of n, linear convolution result. That's equal to x1 of n linear convolution with x2 of n. Okay, so you people might have seen these are kind of rectangular sequences. When you convolve them, you get a kind of triangular sequence if you convolve them. So I will sketch directly here. Just check yourself whether what I'm sketching here is does it make sense. So it will flip. Okay, if you see, this will come here, flip here. Okay, 0 -1 -2 -4 it will be. Okay, and then it will slide here. So till it comes to 0, there is no like overlap. Once this signal after flipping also comes here, overlap will be 1. If it comes here 2 3 4 5, it increases up to 5 and then start decreasing. Okay, and then 4 3 2 1 0 kind of thing. Okay, so we can directly write in this example. Those who are not familiar with convolution, suggest you people to be clear. Okay, let us write here. So let somewhere 0 be here. Okay, 1 2 3 4 5 6 7 8 9 10. Okay, now so this 0 is 1. Right, and then fine. So 2. Okay, my 1 is itself is high, right? So let me, for the sake of simplicity, let me sketch this with magnitude 1 being only this. Okay. Okay. 1, height of 1. Okay, I'm showing height 1 also like this. My drawing later will be simpler. Okay. Right. Okay, magnitude is 1. Each sequence. Okay. Now let us sketch. This is 1. The overlap starts from when this gets flipped and get started sliding. Overlap starts from 0. Okay, that's why 1 here. And then 2, 3, 4. And overlap is maximum at 4 and it is 5. Value is 5. Start decreasing. start decreasing and decreases and reaches to, okay, so yeah, here 2 1 2. So now the sequence is 9. Okay, so it is n1. So this linear convolution, so length of this is, so n4 I would say is equal to n1 plus n2 minus 1, which is equal to 10 minus 1, that is 9 samples, as you can see here. Okay, 9 non-zero samples. Okay, this is one, and you can understand the others. Okay, right? Okay, so now this is the result which we have, right? Now what we want to see is how does the circular convolution result look like. So we will compute the circular convolution explicitly. Without computing the circular convolution, let us use this expression, okay, to write, to understand how should be the circular convolution result. So that expression, what it says is, okay, x3 tilde of n is equal to summation, that is periodic shifts of x4 at, okay, rn, and r equal to minus infinity infinity, and from that if we take one period of it, okay, that is x3 of n is equal to, okay, one period of it, right? So how do we write that is, x3 tilde of n we write as x3 of n modulo n. Okay, so if it goes out of this, then x3 has one period of x3, okay, and with modulo n operation gives x3 tilde of n. Okay, that means if it is n, so a small n equal to n implies that modulo n operation gives, okay, x3 of 0. X3 tilde of n, sorry, imply x3 tilde of n is equal to x3 of 0, because it repeats, right? So this periodicity can be written as like this compactly. Okay, if you want to relate the periodic sequence and aperiodic sequences, we can write through modulo n operation. Okay, if they are one period of it is exactly same as this aperiodic sequence. Okay, so please note that similarly you can write actually n equal to n plus 5, for example. Okay, implies, okay, so x3 tilde of n plus 5 is equal to x3 of 5, right, like that. Okay, and so on. So, and this gives us one period of, that implies now this is one period of x3 is equal to, okay, what will happen, x4, okay, of whichever, see in this, which are the terms which will be non-zero, see, which will have overlap in 0 to n region, those terms we have to consider while writing this x3 of n. So given this understanding, let us try to write directly, sketch x3 of n. Okay, so how to sketch x3 of n? Let me try here. So I will start from 0. Okay, so let us have a, so which are the ones which will first be like non-zero in 0 to 4 region? Let us see. For what range of n? Okay, we get some samples in 0 to n region. Okay, 0 to 4 region for this signal. R equal to 0. Anyway, we have the sequence x4 of n here. Okay, this itself I will write clearly as x4 of n. Okay, right. And now if r equal to this r equal to minus 1. Okay, that means it starts from where, r minus 4. Okay, so 5, right, minus 5. So if it starts from minus 5, will there be some samples in this region? The answer is yes. So r equal to minus 1 also has some samples here. R equal to plus 1. That means it starts from 4. Okay, or it starts from 5. There are no samples that comes in this range, right? So for writing in this range, r equal to 0 and r equal to minus 1 will have some overlapping samples. Those are to be added, right? So I will write now the explicitly. Let me see if I can write with different sketches. So this one has two components. So r equal to 0 case. Sorry. I will write the expression and then write this summation. R equal to 0 and 1. Okay, so because r equal to 0 and 1 only have the samples here. Remaining have no samples in this region, x4 of n minus rn. Okay. Samples in 0 to 4. Okay. Span of x3 of n. Okay. In span of x3 of n. Okay, because x3 of n, as we know, is obtained from where? So I will write the relation for x3 of n. So please note that the x3 tilde of n has come from x1 tilde of n. Okay, circular convolution. Okay, with x2 tilde of n. Similarly, x3 of n we have defined as x1 of n point convolution with. Okay, with x2 of n. Okay, please note that from this we have got this. Okay, x3. So from these two, right? Okay. So and now we want to relate this to x4. That's our discussion now. And the span of this is the length n. Okay, length n is equal to 5 here. Okay, 0 to 5, 0 to 4 here, right? And hence, so what should I do now? I will pictorially try to depict here. Let us see if we can do it. 0 to 4 region, right? So let me, I think it will be too much crowded if I do here. So let us move to the next slide and try to get x3 of n from, this is time aliasing if there is an overlap. Right. So let us now write x3 of n is equal to summation x4 of n minus rn. R is equal to 0 to 1, where x4 of, say, let us bring in the same color. X4 of n, let it be as given before, 1, 2, 3, 4, 5, 4, 3, 2, 1. Okay, 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, fine, 0 to 9 samples. Okay, now what we should get is x3 of n through circular convolution. So it is, what we are saying is it's time aliased version of this. So let us sketch this. So first let us sketch x4 of n is here, right? We already sketched it. So let us make use of it. Okay, so now let us sketch the other version of it. So it is x4 of n minus, r equal to 1, right? N minus n. That means where should it start? It should start from, okay, it should start, this is 0, right? 0, minus 1, minus 2, minus 3, minus 4, minus 5, 6, minus 7, minus 8, minus 9. Okay, so x4 of n is how much? Capital N equal to 4. Okay, capital N equal to 4. Sorry, capital N equal to 5. And hence it should start from 5. Okay, so minus 5 it should start from. 0 has to come from 5. So where, okay. Sorry, I think, so if it n equal to 5, the shift will be in this direction. So let us bring in, okay, minus 1. So it has to be 0 and minus 1. Okay, because n plus 4 will bring in this side. Okay, n plus 4 will bring in this kind of shift, right? So we'll bring in here, just the discussion is same, but here what terms we should consider is -1 and 0. Okay, 0 and -1 otherwise. Okay, so now 0 -1. Okay, it's fine to add first 0 and then -1. Okay, so now where does it start? It should start from -5. Okay, so -5. So the same sequence has to come 2, 3, 4, and then 5. Okay, and then 4 here. Okay, 3 here, 2 here, 1 here. Okay, 0, 1, 2, 3. Am I correct? Shifts by 5, and hence, okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. N equal to -5. Okay. So the sequence length is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Fine. Right. So now this summation, if we do these two, if we add, okay, if we sum them, okay, but in what range should we see for getting the x3 of n? We should only see in the range, okay, 0, 1, 2, 3, and 4. Okay, and hence we should only look in this range. So the answer is here 4 plus 1, that is 5. 1, 2, 3, 4, 5. Okay, 3 plus 1, 3, sorry, 2 plus 3, that is again 5. Okay, this is equal to again 3 plus 2, that is 5. 4 plus 1, that is 5. You see here, this is what I am adding, these two, these two, these two. Okay, sequences. And 4 plus 1, that is 5. Here 5 plus 0, that is 5. And we restrict to this range for getting, sorry, 0, 1, 2, 3, 4. I'm done. Okay, no need to go here. 0, 1, 2, 3. Yeah, I'm done. Okay. So this is the sequence x3 of n, right? Obtained by x4 of n plus x4 of n plus n in this case, right? We advanced the signal, right? Okay. So, sorry, this is plus. Okay. So, right. So, in the region of the sequence, wherever there are non-zero, like wherever there is a overlap, that tile, okay, that periodic, that shift we have to consider for writing time aliasing, okay, for x3 of n. So you can see that you got x3 of n through the linear convolution. What we have got is circular convolution from linear convolution. This is linear convolution result. And this is circular convolution result. Okay, now let us take the sequences and see if we do circular convolution, what do we get? Okay, whether is this correct? Okay, so for doing that, let us bring in here itself. So x3 of n. So let us perform circular convolution. For x3 of n, right? That is x3 of n is equal to x1 of n n point, here 5 point, x2 of n. Okay, n equal to 5, right? And you also know the samples. Okay, so see, for circular convolution, what did we say? We take the sequence x1 of n, okay, which is, say, for example, like this: 1, 2, 3, 4, 5. 0, 1, 2, 3, 4. Okay, so and the sequence x2 of n, and then circularly shift the sequence, other sequence, and start convolution. So the expansion we write here: x1 of n, x2 of n, m n minus m, m equal to 0 to n minus 1, right? This is what we have written for x3 of n. Okay, so n also is varying from 0 to n minus 1, right? So now what do? We take the first sequence, second sequence, flip it first, because the index is m here, running index is m. Okay, sequence index is m. So we flip it first and shift it by, okay, n units. Okay, n may be 0 for initially, but in that case, it may not be in the range 0 to n. So we apply modulo n operation. Then we said it is equivalent to, okay, circularly shifting. So first let us write the expressions for, okay, so this is what we x2 of, okay, expressions for x2 of minus m, x2 of minus 1 minus m, and so on, and then apply this. Okay, so let us do that. Let me write with a slightly different color. So what we have here is x1 of n. Okay, so now let us write x2 of minus m. Okay, minus m or minus n. Okay, minus m, let us take the running index to write this. This let it be m. Okay, for writing this convolution sum. Okay, now say minus m if I want to write, but I want to do with modulo m operation. Modulo n operation. Okay, see, if I directly write minus m, what will happen? The sequence will start from 0 and it will be in this direction. But now if I apply modulo m operation, okay, the whichever is here, so n minus m will come. So we should take care accordingly. You can note that with n minus m. So you can see these sequences. Say, to write this easily, you can assume that there is a circle. Okay, and the sequence indexes are x of 0 here. Okay, x of 1 here. How many samples are there? 5 samples. So let us divide the circle into 5 parts. Okay, 2, 1, 2, 3, 4, and 5. X of 1, x of 2, x of 3, x of 4, right? And 5. Now, x of minus m means what? Okay, you take x of 0, x of minus m modulo n means I will directly write from the circle. Okay, so x of minus m, if I want to write, how do I write is, okay, 0. Okay, whatever x of 0, I will write the sequence number also here. Okay, x of 0, what I get at index 1. So let me write the sequence number on the top. Okay, 0 and x of 0. What I have put is x of 0. And 1, what should I write? 1, I should write it as this sequence. Okay, so x of 4. X of 4, right? At 2, what should I write? X of 3. And yet 3, what should I write? X of 4. Okay, x of 2, sorry. 2. And then what should I write here? So let me write with slightly different colors for this 0. Okay, let me write the 4. So this is x of 0, x of 4, x of 3, x of 2, x of 1. Right? As you can see, there is a circular shift here. Okay, you can see like this and you can write this. So what I'm writing here? What I'm writing here is x2 of minus m, okay, modulo n. Okay, is this. Right? So this and this, when multiplied together, that means these two, okay, when I perform convolution, dot star and sum them, okay, and sum them, that is convolution operation. Okay, so I just briefly wrote like this, but please understand that the whole convolution operation, element multiplication and convolution has happened, is equal to what it gives? X. So let me write with again different color. To avoid confusion, let me erase. Okay. Oh, very good. Okay. So let me erase these as well. Okay. Okay. So x of, let me select another color. X of x4 of, okay, because I want to write the convolution result, x3 of 0, I will get like this, is equal to how much? If I just multiply, element multiply and sum, the answer is 5. Okay. Similarly, now what I want to write is, okay, let me write the next one. So x2 of 1 minus m. To compute, what I want to compute here? I want to compute x3 of 1. Okay, to compute this. So what will it be? It will be again same sequence as you can see here in this example. 1, 2, 3, 4. But x1 minus m is, see, m equal to 0 if you put here. What I have is x1. That means instead of starting now from here, I will start from here. Okay, and then but in reverse direction I will go. Okay, so x of 0, x of 1, x of 1, x of 0, and x of 4. Okay, and then x of 2 will come here. Right? You can see like this. Now, with respect to this, if I take, okay, this, okay, this gets multiplied with this, okay, element multiplication and sum, to get what? To get x3, I will write with this, x3 of 1 is equal to how much? 5. Right? Similarly, you can see and so on. You can also see, okay, I will directly write here for simplicity, okay, x2 of 4 minus m, because the maximum value it goes is up to 4 n. Okay, what is that? What I get will be 1 1 1 1 1 0 1 2 3 4, but 4 minus m is x of 4. It starts with x of 3, okay, and this x of 0, and this is x of 1, okay, x of 2 in between. Okay, like this. Now there is a circular shift. x4 minus m means, okay, it starts from here but goes in reverse direction. Okay, that's what is his. Okay, and this multiplication with, okay, this I will directly write here because of the less space, the dot star with x1 of n, okay, and summation gives what? Gives x3 of 4, which is also equal to 5. Okay, thus this implies, you can see that, okay, this implies, you can see that x3 of n is equal to, okay, 5 for 0 less than or equal to n less than or equal to 4, which is exactly equal to circular convolution result. Okay, through circular convolution, time domain circular convolution is equal to whatever I have obtained from linear convolution. Okay, so as you can see here, through this is obtained through circular convolution using the time domain aliasing of using linear convolution and time domain aliasing. Right? So the results both are same, and you can see that this relation is valid between this is circular convolution and linear convolution, and thus this is the relation would use the between circular and linear convolution. Okay, this is the relating linear and circular convolution. Okay, right. So now there is one more point here to discuss. See, we have obtained in the case where we have, say, let us take the same scenario where we have x3 of x4 of n, which is equal to x1 of n convolution with x2 of n. Okay, and this is discrete time Fourier transform. Okay, and what you got is x1 of e power j omega and x2 of e power j omega, and we refer to as x4 of e power j omega, and we at the parallelly we have got x1 of n, same aperiodic sequence with periodic convolution. Okay, so we have taken circular convolution and x2 of n. Okay, dft. Now the question is, see, can we get the linear convolution result from the circular convolution? That is the discussion. So previously what we have seen, how to get the result of circular convolution, okay, from the linear convolution. Okay, now the question is, can we get okay circular convolution from linear convolution? Okay, by performing linear convolution. Is the answer yes or no? See, linear convolution, the limitation what we have seen is, okay, the linear convolution, the length what we have seen is here, length of sequence is 2n minus 1. Okay, even though the length of these, both of them are n, okay, the length of this is this. So to get 2n minus 1 samples, even in even through circular convolution, what should we do? What we should do is simply pad x1 of n and x2 of n with the remaining samples with zeros, and then make their lengths also 2n minus 1. Okay, so what we say is initial lengths of these two samples, okay, length is n and n, but padding with n minus 1 zeros, okay, it gives the length to be 2n minus 1 and 2n minus 1. In that case, we can assume these x1 and x2 to be sequences of length 2n minus 1 with n non-zero samples. Correct? Why are we doing this? See, at the end, to get the linear convolution, at least we need, okay, 2n minus 1 samples at the output. To get through circular convolution, if we would like to get 2n minus 1 samples, what we should do is, we should do circular convolution with what? With 2n minus 1, okay, 2n minus 1 point circular convolution we have to do, right? That if we do, okay, then we will be, okay, then what we get is x3 of n of length, what? Of length 2n minus 1, because this length doesn't depend upon the length of the sequence, but depends upon the length of circular convolution, right here, because you will be keeping zeros in between and then circularly shifting, okay, and hence the summation also goes up to 2n minus 1, okay, and hence the length of this will be 2n minus 1. Here also, here it is, okay, 2n minus 1 naturally comes, there is no padding of zeros, Okay, so at least we are able to match the lengths of x3 of n, okay, and x4 of n in lengths, by making padding initially with zeros for these sequences, okay, and then making 2n-1 point circular convolution. Now the question is, if I now write, okay, x1 of k and x2 of k, multiply them and get x3 of k, okay, and we assume that this x3 of k be sampled version of x3 of e power j omega, yet omega equal to how many samples we should get? See, these lengths are n. Okay, this sequence length is also now, okay, this sequence length is also n. But however, by padding with zeros, we'll give in how much? The length of 2n-1. Because in frequency domain as well, you will have 2n-1. It's the length of n, x1 of k and x2 of k also becomes 2n-1, right? And then the multiplication also gives 2n-1 samples with padding of n-1 zeros. Padding of zeros means you will put zeros after n samples, okay, to that length to match this length. So if this is the length 2n-1, to get x3 of k, how many samples we should take, or like what should be the sampling free period? 2 pi by n 2n-1, okay, into k. This is very important point. Please note that we are now sampling 2n-1 samples in the frequency domain. Why are we sampling that? To avoid, so you can think in two ways. One way is to get the same length of the sequence at least here, and then we wish to see if we do that, will we get or not? The answer is yes, because if we sample 2n-1 places, then we essentially avoid any time domain aliasing here. That stems from sampling of frequency domain. Please, that can be noted by writing time domain relationships. So let us write x3 of n. What we have is equal to x4. Sorry, this is x4, right? Sorry, x4. Okay, here it is x4 are equal to minus infinity infinity x4 of n minus rn. But n is how much now? This n is the like with what we sample, that is equal to 2n-1. Okay, so this you can consider as n dash or whatever. Okay, so this can be considered as n dash if you want, then 2n-1. Okay, so what will happen? What is the length of sequence x4? Length of sequence is 2n-1. Okay, and hence there will not be any time domain aliasing. Okay, so to write in different notation, if we denote this as, so m, okay, equal to 2n-1, then we write it as, okay, omega equal to, okay, if we sample x4 of, I will write only omega here, omega is equal to 2 pi by m into k. Okay, in this case, n is equal to m and no time domain aliasing. What is this n? N dash L, right? Because sampling in frequency domain. Okay, sampling in frequency domain, number of samples in frequency domain matches the sequence length. Okay, originally, so there is no aliasing, right? So that means, so if you take now one sequence, you will directly get it. Okay, since there is no aliasing, no time domain aliasing, we get x3 of n. Okay, what we get here is x3 tilde of n. What we write here is x3 of n. We can write x3 of n is equal to x4 of n. Okay, right. So that you can see. So you get through circular convolution, that implies x1 of n circular with 2n-1 and x2 of n, what you get is equal to x1 of n linear convolution with x2 of n when x1 of n comma x2 of n are of n length sequences. Length n. Okay, right. So to conclude this discussion, let us write in general case. In general, okay, circular convolution result is equal to linear convolution if, okay, if we avoid time domain aliasing to say if x1 of n comma x2 of n with lengths, okay, n1 comma n2 or circularly convolve at n1 plus n2 minus 1. Okay, n1 plus n2 minus 1 points. Okay, because there will not be any time domain aliasing. So even if we convolve with more number of points, it is fine, but it is not necessary, right? So this is the relation that helps us to get either from the circular convolution to linear convolution, or okay, circular convolution to linear convolution, okay, through more point circular convolution, or from linear convolution to circular convolution from taking advantage of time domain aliasing. Okay, the both of them can be computed by direct methods as well through their expressions. That's all regarding the properties of discrete Fourier series, Fourier transform, and connection to discrete Fourier series and discrete time Fourier transform. Thank you.